Hello. In this lecture I'm going to talk about the cosmic microwave background radiation, the radiation field that permeates the universe and to a great extent provides the best cosmological information we have. It's essentially a radioastronomical and principally millimeter wave radiation field today, but we'll see it's been through a number of changes. I'm going to talk in 4 sections based about 4 developments really in microwave background radiation discovery. Firstly, the initial discovery and the interpretation of the radiation, and I have to go back to the beginnings of general relativity to show where that comes from. Then I'll talk briefly about 3 experiments, the COBE, WMAP and Planck satellites, show you the sort of information that we're getting from the microwave background radiation today, and sketch out some of the interpretation that is possible from it. I'm going to do this divided up into 3 or 4 shorter lectures so that there's time for you to think in between. So let's start with a discussion of the history of the radiation. This really starts with the discovery done by Bob Wilson and Arno Penzias using a rather weird-shaped radio telescope at Crawford Hill in the US. It's behind them there. This horn antenna was being used to look for a source of excess noise that was showing up in radio communications. After scraping various bits of pigeon droppings out of the antenna, which they thought might have been providing some of that excess noise, they were able to show that at 7.35 centimeters radiation, the excess noise seemed to be almost uniform over the entire sky. The origin of that excess noise was initially not very clear to them. However, it had been predicted some years before. In 1948, Gamow and Ralph Alpher had written a paper on Big Bang nucleosynthesis, the origins of the elements in a very early hot phase of the universe, something predicted by the general relativistic equations of motion of the universe. And in work that took in Robert Herman, had been able to show that if you believe that the universe started hot, certain elements would have been produced in the early universe, and the heat would then have spread out as the universe expanded to produce a rather uniform radiation field at a temperature of some tens of Kelvin. That tens of Kelvin calculation was based on early cosmological parameters, and when you improve the calculations you get something closer to 3 Kelvin. And that was going to be the interpretation of this excess noise that Penzias and Wilson found. Let's switch to Princeton University in 1965, because at about the same time that Penzias and Wilson were searching for their excess noise, Robert Dicke and his students, including David Wilkinson, were looking for the background radiation predicted by Gamow, Alpher and Herman. They were informed about the work that was going on at Crawford Hill, not very far away from them, when the people at Crawford Hill contacted them to try to find out what they were looking at. They realised they'd been scooped by Penzias and Wilson. I've written down Wilkinson, I meant Wilson. But were able to write the interpretation paper for the radiation that Penzias and Wilson had seen in a companion paper to the Penzias and Wilson paper that announced the discovery. So discovery by Penzias and Wilson, and interpretation by Dickey and Wilkinson. Now, what was that cooling of the radiation field? Well, now we have to jump back to 1922 and the chap on the left here, Alexander Friedmann. I've written his name out in Cyrillic since the transliteration that's used doesn't do justice to his name. He was working at the Perm University, and very soon after the equations of general relativity were spelled out, he showed that the basic solution was going to be an expansion. Now, a modern version of that solution is shown in the figure on the right, where on the x-axis I've put time, scaled by the Hubble constant, and on the y-axis I've put the size of the universe. If we start the clock running at time 0, at the far left of that axis, the universe was then of 0 size. As it expands, the effect of gravity is to slow it down, because gravity tends to be attractive and slow things down. That would continue forever, except that we now believe the universe contains a dark energy field which provides late time acceleration. And on the right hand side of the diagram, after the vertical line which marks the present day, you see that the universe is starting to accelerate up. That is, the line is curving upwards. The y-axis here, I should say, is a measure of the expansion of the universe compared to its current size. So the current value would be 1, and I can read off from this solution what the age of the universe is in units of inverse Hubble constant, so in units of about 14 billion years. So for this solution, using the best current physical parameters, I get a number of about 13.6 billion years. So let's use 14 billion years in round numbers. So how do we prove that this radiation comes from the past? Well, that it most likely does is fairly obvious. If the universe started small and expanded, then anything that was in it would have cooled down as the gases and the radiation expand. Back at about 13.6 billion years ago, if you follow the equations, and there'll be a problem on the problem sheet to have you do that, you find that the compression relative to the present is such that the matter within it would have been ionized to a temperature around about 3000 degrees. And when matter is ionized, it emits radiation quite copiously, and at 3000 degrees matter emits red optical and infrared light. As that light is expanded by the expanding universe, the characteristic wavelengths increase. So they increase from, say, 1 micron to the present day, when the peak is in the millimeter range of the spectrum. So we interpret the black body radiation as this emitted light. Now, because at around 3000 degrees the density of the universe was sufficiently high that matter and radiation interacted quite quickly, we expect the matter and radiation to come to thermal equilibrium. As the expansion then carries on, the thermal equilibrium is broken, but the shape of the spectrum is not. You retain black body radiation shape. That's what I've written down here. The matter cooled off and became neutral, and light interacts so weakly with neutral material that effectively, if we look at the microwave background radiation today, we're looking at a picture of the universe 13.6 billion years ago. That means we've got a very direct snapshot of the early universe when we study the microwave background radiation. And I've written down here that the thermal radiation travels towards us affected only by the expansion of the universe, which swells out the wavelengths of the radiation. And that's nearly true. In fact, there are faint interactions that the light goes through. Now I've written down here, I've shown the graph rather, of scale factor against time. Scale factor is an intrinsic measure of the size of the universe, and we can rewrite that in terms of redshift, which is the way we normally express things. And redshift is defined in this notation by 1 plus redshift is the size of the universe today, A0, divided by the size of the universe at the time in the past corresponding to a redshift Z. If I put in Z equals 0 in that equation, so the left-hand side is 1, so A must be equal to A0, that is, the size of the universe is equal to its present size. So redshift 0 is today. Positive redshifts correspond to the past, and as redshift increases, you can see that A gets smaller, the universe was smaller in the past. Negative redshift is rarely talked about, but it corresponds to the future. It corresponds to when the universe is bigger than it is at the present. And if the universe is accelerating away and expanding forever, at the end of time, when the size of the universe is infinite, the redshift will be -1. So redshift tells you the size of the universe at the time that an object that you're looking at that has a redshift emitted that light. And so it also implicitly measures the distance, because it tells you how long the light has been travelling towards you. So we use redshift in a number of ways, one of them being a measure of date, time since the beginning of the universe, time since the present, and one of them being as a measure of distance from us. Those things are interchangeable. Here's a plot which shows how the temperature of matter and radiation in the universe would have changed with redshift. This is a logarithmic scale because there's a lot of change. The present day has redshift 0, so log of 1 plus redshift is 0, and that's the dashed vertical line, which I've labelled now. The blue line shows the temperature of matter in the universe. The red line shows the temperature of radiation. That radiation is the microwave background radiation, and it follows a nice steady drop since the very early days of the universe. Matter, on the other hand, cools with the radiation when radiation and matter are dense enough that they interact very strongly. But after that, when matter and radiation stop interacting, the matter cools faster. And so matter today would be predicted to be rather cold, except for the fact that since about redshift 10, there's been structure in the universe, stars. The matter has clumped together into dense lumps which have then been reheated by nuclear physics. Essentially, the gravitation of the matter has heated up the material so that it can fuse, and that has then released energy into the universe and reheated matter. We call that the epoch of reionization or reheating. Now, there are a number of details that we need to be clear about here. The first one is the background radiation really a cosmological thing? I've asserted that it is, based on the measurements, the uniformity, and theory, but we better prove it. And a good way of proving it would be to find out whether foreground objects cast shadows. So we can find a very distant object. If that casts a shadow on the background, it really proves the background originated beyond it. We can check whether the radiation field really is thermal. That is, does it look like an expanded version of the radiation you get from dense early matter? And you can check whether the background radiation is entirely uniform. If the universe started at a point and then expanded, then everywhere was in the same place originally, and you would expect the background radiation to be very uniform in brightness and temperature, unless, of course, some structure started to form in the material and then changed its properties. So measuring the angular structure of the radiation is really quite a good thing to do. Now, shadows in the radiation field have been known about for about 40 years. They're the Sunyaev-Zel'dovich effect, which I'll be talking about later today. And in brief, clusters of galaxies contain hot gas, and the passage of radiation through that hot gas slightly alters the brightness of the background radiation. Effectively, this is the same process of scattering of the radiation that happens to make the radiation thermal in the first place. But here it's a different gas field that the radiation is passing through than it originated in. So the behavior is a bit different. And after a brief pause, I will start again and talk about the COBE satellite, which started to provide detailed information on the properties of the radiation field under some of the other categories.